Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 76, and this question asks us to explain the reactivity and orientation observed in each of these heterocycles, one of them being pyridine, one of them being pyrrole. So in A, it tells us that pyridine is less reactive than benzene in electrophilic aromatic substitutions and yields an addition product or a substitution product at carbon 3. So why is that? Well, let's look at pyridine. So pyridine is similar to benzene, except it has this electron withdrawing nitrogen within the ring. So because of this electron withdrawing nitrogen atom, it actually makes these pi bonds in the ring because of the inductive pull towards the nitrogen atom. It actually makes these pi bonds in this ring more electron poor. So we know that in electrophilic aromatic substitution reactions, these pi bonds must be electron rich to be able to act as good nucleophiles to attack your electrophile. However, if nitrogen is pulling electron density away from these pi bonds onto itself, this is making these pi bonds electron poor, and therefore it's going to react slower or more poorly than a benzene ring itself. Also, the electrophile can be attacked by this nitrogen with its lone pair electrons on itself, and that will put a positive charge within this ring, which would make the ring less reactive with another species. So if you see that, if we attack the electrophile, now we have a positive charge inside the ring, which is not that stable in electrophilic aromatic substitution reactions. But now to understand why reaction or the addition occurs on carbon 3 and not on carbon 2 or 4, let's look at the resonance stabilization for when we have a carbon attacking or the electrophile attacking or adding on carbon 2 versus on carbon 3. So let's say we're adding it on C2. So we're adding it through this carbon atom picking up the electrophile. So right away, if we were to do that, we would see that right off the bat, you get a positive charge on nitrogen, and that's not that favorable. But now nitrogen can move its lone pair electrons here, and sorry, let's redo this. So let's actually start off with something that makes it easier to see. So we'll actually draw the lone pair here. Sorry. So we'll draw the carbocation on this carbon here. And now this actually makes it a lot easier to visualize. So now with this carbocation on this carbon atom, we can go through some resonance structures, moving these pi bonds around. And we can continue moving these pi bonds around. Remember, resonance have double-headed arrows separating them. So now this makes a lot more sense. Now we have a positive charge on this nitrogen atom. So here in this resonance structure, nitrogen does not have a full octet. This positive charge on this electronegative nitrogen atom makes this a very poor resonance stabilized structure, and it's not that favorable. So, but now let's see what happens if attack occurs on carbon 3. So if attack were to occur on carbon 3, on this carbon here, then we would have carbocation over here, in which this pi bond can come on this side. So make a positive charge over here, and then this pi bond can come over here to move that positive charge around. So in this situation, we still have 3 resonance structures, but now in this case, none of these resonance structures puts a positive charge on our electronegative nitrogen atom. So by virtue, attack on carbon 3 makes a more stable carbocation than attack on carbon 2 or 4. So that's why attack will occur on carbon 3, because we don't have any resonance stabilization by putting a positive charge on electronegative nitrogen atom. All these positive charges are on the carbon atoms of Pyridi. So now in B, it asks us, pyrrole is more reactive than benzene in electrophilic aromatic substitution and yields addition on carbon 2. So why is that? Well, let's draw pyrrole. So pyrrole itself can actually donate electrons into the benzene, into the aromatic ring, to form an electron-rich carb anion in the ring. So now you're making this aromatic ring more electron-rich. And this is through the lone pair of nitrogen electron donating through resonance structures. So now we have a carbanion in the ring. So this by virtue makes the ring a better nucleophile and therefore more reactive than benzene in electrophilic aromatic substitution. And we can also move this carbanion around throughout the ring. Carbon ions over here. So let's see what happens if attack occurs on carbon 3 instead of on carbon 2. So if attack goes through this carbon, pick up this electrophile. Then we can use nitrogen's lone pair electrons to now make a pi bond here. But then all of a sudden, that will put now a positive charge on nitrogen, which in the case of pyridine, we determined that's not favorable. And if I were to move this pi bond here, I would just get back this original structure, which we initially drew. So there's 2 resonance structures if we have attack on carbon 3, but what about attack on carbon 2? And one of those resonance structures on attack on carbon 3 has a positive charge on nitrogen, which we already determined is not stable. So on the other hand, on contrary, if we had attack on carbon 2, now we have a carbocation up here, which we could resonance stabilize. And then one of them, yes, can be with the positive charge on the nitrogen atom. But already there's already one more resonance structure than if attack was on carbon 3. So already we know that this is going to be a lot more stable than attack on carbon 3. So because of this, we have more resonance structures when we have attack on carbon 3. Therefore, we have a more stabilized carbocation, and therefore electrophilic substitution will occur on carbon 2 and not carbon 3 for pyrrole.